So for the first...
Okay, ich lasse einfach laufen, dann kann man schneiden, ja.
Okay. So the first question, how long does it take to fly a rocket out of the atmosphere?
A rocket leaving the atmosphere, for example, reaching ISS. ISS is about 400 kilometers away from the surface, 400 kilometers, and it takes about 6 minutes to reach there. But it's very Earth near. This is an orbit. The ISS is circulating in an orbit very, very Earth near, 400 kilometers. It's not so far. You see it at night. You see it pass by. The dimensions are much more. You know that the light speed is the fastest speed of existing, and maybe you know that the sun, the light of the sun, needs 8 minutes to come to Earth. We are at a distance to the sun, that the light needs 8 minutes to come here. If somebody turned out the sun, we would notice it 8 minutes afterwards. It would be dark.
So it's basically a question about the distance between the start and the end point.
No, no more.
Also im Endeffekt, ich habe gerade gefragt, ob es im Endeffekt einfach sinnvoll so ist, wenn der Startpunkt und der Endpunkt, also wie weit die Entfernung ist, die Distance. Okay. So basically it's a question about the start point on the Earth and the distance between the point do you want to reach.
Yes, that's of course. It's a distance in kilometers or in light years or whatever.
So why and when did you think or decide to study mathematics?
Maybe when I was about 15 years old, I had a very smart teacher showing us vector calculus, and that was very interesting for me. Before that, I didn't have so much problems with mathematics. It was quite easy for me, but that was a moment where it was a very enthusiastic teacher, and he showed me, and it was fascinating for me. From that time, I went in this direction, let's say.
Why does an astronaut need mathematics?
The astronaut does not need mathematics in his work. Alexander Gerst, who is now in the ISS, will not take his block and calculate some equations or something like that. But to be an astronaut, you have to have certain prerequisites. You have to have studied, for example, physics, engineering, aerospace engineering, geophysics, something like that, or mathematics maybe. And for that, you need some mathematics. All these studies need a mathematical background. You cannot be an engineer without avoiding mathematics. That's impossible. And it would not be so good if an engineer did not know mathematics.
So is school mathematics equal to mathematics you do while you study?
No. The school mathematics is, let's say, it's a kind of philosophy. You learn methods, you learn, of course, basic technologies, calculating this and curve discussion, these things. But it's basically the gain from school is to learn methods, to learn a certain kind of thinking, approach to problems, an analytic approach to problems. That's what is the mathematics worth for afterwards in the different professions. The ability to abstract, to have a problem and not only see this problem itself and calculate, but to abstract and find maybe new solutions, mathematically new solutions. A very good example is the Mars project. You know that people want to go to Mars sometimes, and up to the 90s, the calculation of a possible Mars mission had a a starting window of 2 years. It means the constellation of Earth and Mars had to be on a certain kind that only happened every 2 years. And then it was in the middle of the 90s, I think, two Italian mathematician found a possible other way to approach Mars. The big problem of this kind of missions is to take away the acceleration. When you approach the other planet, you must brake, you must slow down, and this costs a lot of energy. And they found a principle which is called a ballistic capture. That's a way approach when the aircraft, the spacecraft, reach Mars on a new way that Mars comes from behind faster than the aircraft, and it's a gravitational absorbing. He absorbs, he breaks down, and this gives new possibilities to calculate a new path. And this journey is not yet possible only every 2 years, it's more often possible, and it costs much less energy. Very interesting mathematician. That's what I want to say. What you gain is the ability of separate a bit from the problem and see the other context and understand the principles behind and find new ways. It's interesting.
Okay, really interesting. Just which content of school mathematics, for example, functions, calculations of differentials and integrals, vector calculation and the third dimension, do you need for aerospace engineering?
Yes, exactly what you told. That's what's called calculus, infinitesimal calculation, integrals and derivations. That's what's most important. To have a concept of movement in space in 3 dimensions, acceleration, forces, and all these things is very important. To have a clear concept of what happens there. Therefore, vector analysis and calculus is most basic. The other things also, matrices, for example, is very important because all the movements, all the equations on which movements are based are nonlinear equations. And a nonlinear equation is not, you cannot solve algorithmically, you have to solve it numerically. And all numerical approaches are linear. And for linear equations you need matrices. And therefore it's, almost everything is important, but the calculus is the most.
I had just another question. Do you really calculate in the 4th dimension for aerospace engineering? Because the time is a very important factor.
The time is important, yes, of course. The idea of the 4th dimension is a bit utopic. The velocities, we saw it in your first question, is not so relevant for these calculations because it's very, very slow compared with light velocity. For example, a far journey of a spacecraft accelerating unmanned, without people on board, can accelerate very fast, but the influence of relativistic influence is far beyond 1%. So this idea of the 4th dimension and the curvature of the space is not so important theoretically, but for the calculation of paths in the Earth, it's there, but it's very, very minimal. Therefore, the calculation is basically 3-dimensional.
Okay. Just the last question for today. What do you wish, or what do you think a person who has finished school should know about mathematics? Or which content this person should know about mathematics and about calculation?
I think ministries and schools give a broad base of mathematics nowadays in schools. So the people finishing school have a if they studied well, they have a good broad base to do almost everything. So the mathematical concepts, I said before, calculus is maybe a bit more important, but it's not crucial. I think the crucial gain you have from your school is to have learned to learn, to have learned to abstract problems, to approach problems, to not give up, to not avoid a problem, solve it. No? This kind of steadiness, that's most important. That's what gives mathematics, I think. Therefore, I think mathematics is basic, not only in the technical meaning, but also in the mind of the people. It's important to have learned this concept. Abstraction is very, very important. To know to abstract, to see the problem, but not only to solve the problem itself, but to understand the surrounding of the problem, the border conditions. Maybe an example, very, very simple example from basic school. Let's say you have a child and you ask him, maybe he knows already some calculation. What is 2 apples plus 3 apples? He says 5 apples, okay, very good. You ask him 1 pear plus 3 pears, so 4 pears, very good, very good, very good. And then you ask him, what is 2 apples plus 2 pears? And he says 4. And you look, for what? And then he makes his eyes big, and then he says, for fruits. And that is abstraction, you know, to take a bit of distance from the problem and to see what is the concept behind. In a simple example.
So that's me.
Thank you.
Thank you. Well, thank you for your time and for the information you give to us, and hope you have a nice day too.
You're welcome. Thank you.
Und Katz.